So let's look at some examples where we're trying to find these partial derivatives. So let's look at this first part, part A. I want you to find fx and fy, first partial derivatives for the function 3x minus x squared y squared plus 2x cubed y. So let's start with fx. So we're going to take the derivative of 3x, and that's just going to be 3. We're taking the derivative with respect to x here. And now if you look this next term, I have x squared, y squared, but this y squared, it's just a constant. So really you're just going to take the derivative of the x squared, so you'll get 2x y squared. And again here, this y, this is just a constant like 2. So then the only part I need to take the derivative of is x cubed. So we're going to get 6. This will bring the 3 down, 6x squared and the y. So that is fx. Now let's find fy. So I'm going to go back now. Let me erase these things that I've underlined. Okay, now we're taking the derivative with respect to y here. Well, 3x, this is just a constant, so the derivative is 0. And then over here, I'm now viewing x squared as constant, and I take the derivative of y squared, so it'll be minus, and you bring a 2 out in front, 2x squared y. Again, we're viewing x as constant, so this whole thing in the front is constant. So I'm just taking the derivative of y, which is 1, so it'll be 2x cubed. And there's my partial derivative with respect to y. So let's look at another example. Find fx and fy for the function ln of x sine of x squared y. So we're going to find fx first. Well, if you look, I have a product, and both of these things involve x in them. There's an x there and an x here, so you're going to have to use the product rule. So I copy the first one down, ln of x, and then I need to take the derivative of sine of x squared y. So if I look, this is going to be a chain rule. There's an outside and an inside here. So the derivative of sine, it's cosine. And I need to multiply by the derivative of the inside, but I'm taking the derivative with respect to x. So what's the derivative of the inside with respect to x? It'll be 2xy. Plus, and now you flip it. You're going to take the derivative of ln of x, which is 1 over x. And then you just copy the second one down, sine of x squared y. And there's my partial derivative with respect to x here. So now let's find fy, the partial derivative with respect to y. So I'm going to go back and I'm going to erase the things I've underlined here. So now, if I look, there's only a y involved in this last term here. So this ln of x, this part in the front, that's just a coefficient here. So I no longer have to use the product rule. So the derivative would be ln of x, and then I have to use the chain rule. The derivative of sine is cosine, and then take the derivative of the inside with respect to y, and that would just be x squared. And there is my partial derivative with respect to y. Okay, so real quick, I want to go over the notation that's used. Notation for first partial derivatives. So the notation that gets used is, so if we're using z, we could denote fx and fy are denoted by, so you could also write z sub x there. The same thing for fy, you could write z sub y there. But we also use these other notations. So the partial, that's kind of like a curly D there. It's not a 2. A partial with respect to x of your function. The partial with respect to y of your function. And it's the partial of z with respect to x, and the partial of z with respect to y. Now, if we're evaluating our partial derivatives at a point, so for example, if I want f of AB, another way we could write this is with a vertical line. So you would say the partial derivative of z with respect to x evaluated at AB. And the same thing for fy. Fy, the partial derivative of z with respect to y now, evaluated at AB. So let's look at one last example in this video. So for the function, it's going to be x times e to the x squared y. I want you to find fx and fy and evaluate each at the point 1 ln of 2. So fx, if I'm taking the derivative with respect to x, I have x here and I have x's here. So you're going to have to use the product rule. So I'm going to take x times the derivative of e to the x squared. Well, the derivative of e to the x squared will be e to the x squared y. And then you take the derivative of your exponent with respect to x. So that would be 2xy. And then you flip it, take the derivative of x, which is 1, and then copy the second one down. So there's my partial derivative with respect to x. Let's find our partial derivative with respect to y now. So I'm going to erase these. If I look, y is only contained in this second term here. So that means I don't need to use the product rule. That x is just a coefficient right here. So I don't need to use product rule. And the derivative will be x. And then take the derivative of e to the x squared y. E to the x squared y. But now I need the derivative of the power with respect to y, which is just x squared. Okay, so if I simplify that, fy would be x cubed e to the x squared y. So there's fy, and now I wanted to evaluate both of these at my point 1 ln 2, so you're going to plug that in, e to the ln 2 times 2 ln 2 plus e to the ln 2, but e to the ln 2, the e's and the ln's essentially cancel, so this is just going to be 2 ln 2 plus 2, or 4 ln 2 plus 2. So there's fx, so then I just need fy evaluated at my point 1 ln 2. So if I plug it in, you get 1 cubed, which is 1, e to the ln 2, which is just going to be 2.